Okay, so this is a strange formula that I'm getting ready to show you. I promise you that it is not as difficult as it seems. You just kind of need to understand what it means and how to use it. So this is called Lagrange. It is the Lagrange form of the remainder. So what we're trying to figure out is how close we are to finding the exact value using these polynomials that we've been coming up with. Okay, so let me show you the formula. We'll go through a problem and then I'll go back and explain what it is that we have found. So we're saying the absolute value of the remainder is equal to the actual value, f of x is the actual value, minus the approximation, Pn of x is the polynomial that we find where we've plugged in the x value. So f of x might be like e to the x, and Pn of x might be the fifth polynomial where we had to find the 5 derivatives and you get that polynomial that we've been working out. That's sort of like what that would be. Okay, so we're saying if we subtract the actual and the approximation, that would give us the remainder. Alright, here's the actual formula. It is f to the n plus 1 of z over n plus 1 factorial times the absolute value of x minus c to the n plus 1. Alright, the n plus 1 means it's talking about that particular power. So if I tell you to find the polynomial of e to the x where n is 5, then you have to find up to 5 derivatives and you work out the polynomial. This means that the remainder, you use the next term. So f to the n plus 1 of z means if we were doing that e to the z one where n is 5, f to the n plus 1 of z means find the 6th derivative, divide it by 6 factorial, plug in your x or your x minus c and raise it to the 6th power. The n plus 1 just means the next power or degree than what we're looking for. Okay? So that formula is like just finding the next term that we're used to finding. Okay? Alright, so let's look at a problem. This problem kind of explains the whole process, and then the next few problems probably have less information. Alright. So first of all, it says find the third Maclaurin polynomial for sine of x, which means P3 of x. Okay, this is where we start off with f of x, and we find all the derivatives. Okay, I know f of x is sine of x. The derivative is cosine, negative sine, negative cosine. It says Maclaurin, so I know that I'm plugging in 0 for all of these. Sine of 0 is 0, cosine of 0 is 1, sine of 0 is 0, cosine of 0 is 1, and there's a negative, so we've got that. I know that the formula, that would be 0 plus x plus 0 times x squared over 2 factorial minus x to the third over 3 factorial, which is 6. So that's what we're going to approximate p of 3 of x. That's the polynomial where the degree is 3, and we found 3 derivatives. Now, using Taylor's theorem, that's saying what you can do is you can estimate what we think sine of 0.1 is by plugging a 0.1 into this equation. So we're going to plug 0.1 into that equation, and we're going to get 0.1 minus 0.1 to the third over 6, which is 0.09983 repeating. So P3 of x is an estimation of sine of x. So if I plug in 0.1 into the P3 of x, it should give me something close to what sine of 0.1 really is. And the question is, well, how close really is 0.09983 repeating? I know that we could plug sine of 0.1 in the calculator, and we could look at that. But this particular whole process here with these polynomials is assuming that the calculator is not easily available to us. So the remainder says, since I wanted to find P3 of x, meaning I had to find 3 derivatives, then the remainder has to do with the 4th derivative. So I'm going to go ahead and figure out what the 4th derivative is. I know that if I continue here, the 4th derivative would be sine of x, because the derivative of negative cosine of x would be sine of x. And I'm going to put a z since they put a z in there. Alright, here's the weird part. The weird part is that now we're going to substitute something into this equation up here. Okay, we are going to have f to the 4th of z over 4 factorial times x to the 4th. Now I'm not putting x minus c because I know that c is 0. So I'm just putting x to the 4th. Now, this part on top sometimes is just sort of an estimate. The 4th derivative at z is some value that I know is a big value, the biggest that it could be in that particular interval. Now, with sine and cosine, I know what sine and cosine look like. Sine and cosine, well, sine starts here, goes down and up. Cosine starts up here, goes down and back. The highest value for sine and cosine is 1, and the lowest is -1, always. So for the f to the 4th of z, the 4th derivative of z, I'm thinking about sine, and I know the biggest that sine will be in any interval will always be 1. So when you get to the 4th or whatever derivative that you're looking for in the problem, if you get sine or cosine, you're going to put a 1 in the place of that derivative because that's the biggest value it can be. Now, if it's e to the x or if it's square root of x, you do something different. But when you get sine and you get cosine, then you always put a 1 on top. So you end up with 1 over 4 factorial times x to the 4th. And then you're going to plug a 0.1, because 0.1 is the value that we're estimating. You're going to plug a 0.1 in for x, and you get 4.166 repeating, or 0.7, whichever way you want to put it, times 10 to the -6. This thing is the remainder. So we're saying that our estimate that we have up there, the 0.09983, is off by 4.166 times 10 to the -6, which is really, really small. So that means our estimate's a good estimate. So if you write it out, what that means is sine of 0.1 is less than our estimate that we came up with plus this remainder. I'm not going to write it out because I don't have room right there, but plus that remainder. And that's called the Lagrange form of the remainder. Alright, let's do another problem. Okay, example 2. It says to find the accuracy of the 4th Maclaurin polynomial for e to the -0.1. Okay, I know that I'm finding the 4th Maclaurin. That means I still know that 0 is my c. So I'm going to find out what that polynomial is first. So I'm going to find the 4 derivatives. And actually, I know that since this is e to the x, because x is -0.1, I know that all the derivatives of e to the x, all the way down even to the 4th, are all e to the x. And then when I plug in 0, I know I get 1 for everything. So that particular polynomial, if I work it out, is 1 plus 1x plus x squared over 2 factorial plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial. Now, if I'm trying to find the remainder, my formula is the 5th derivative over 5 factorial times x to the 5th, which is basically the same thing I just wrote, except I went one more step. The remainder says go one more step than whatever polynomial you're looking for. Alright, I know that x is the negative 0.1. I've got my 5 factorial. My question is, what's the 5th derivative of x? Well, if you think about e to the x looks like that. And I know that here's 0, because that's the value, since it's Maclaurin. I know that negative 0.1 is below that. So if I'm thinking about that interval, the y value that's the biggest is at e to the 0, which is 1. So this is another case where you would get a 1 on the top. You will not always get a 1 on the top. I'll show you that in a little bit. In this case, you still get a 1 on the top. So we have 1 over 5 factorial. Plug in your negative 0.1. And you get negative 8.333 times 10 to the negative 8. And so what that tells me is that if I plugged in negative 0.1 into this equation for x, that I would be off. My error would be negative 8.33 times 10 to the negative 8. Now, so I didn't have to do all the red part. I did all the red part to explain a little bit more about the purple and the blue. I hope that makes sense. And I know that you don't want sometimes to hear all the explanations, but I think sometimes they help you. Alright, the next problem. Let f of x be a function where f of x is cosine of 2x plus pi over x. P of x is the third degree polynomial at 0. Use the Lagrange error bound to show that f of 1/3 minus p of 1/3 is less than 100. Okay, f of 1/3 means what I would get if I put 1/3 into here. That's what that means. P of 1/3 means what I would get when I find the polynomial, the third degree, the third derivative, and I work out, and then I plug 1/3 into that. So this is saying that the remainder is less than 1 over 100. So basically, in order for me to prove that, I've got to find the remainder. And so now I just used my formula. Okay? So my formula says, since I'm talking about a third degree polynomial, that I need to know the 4th derivative over 4 factorial times x to the 4th. And it's not x minus something to the 4th, since we know it's Maclaurin because it says x equals 0. So this is the formula, and my x value is going to be 1/3 because that's what they tell me here. The real question is, well, what's the 4th derivative? So let's work it out. Let's figure out what the 4th derivative is. Alright, the first derivative is negative sine, and then multiply by the derivative of the inside, so it's negative 2 sine of 2x plus pi over 6. Alright, the second derivative, you multiply by another 2, so negative 4 sine of 2x plus pi over 6. The third derivative, multiply by another 2. You know what? That was cosine. Sorry. Multiply by another 2, so that's negative 8. It'd be positive. Sorry. I'm running out of room here. I probably should do it on a different slide. And then the 4th derivative would be negative 16. I'm still not doing my sines and my cosines. I'm going to rewrite this on a different slide just so that it's easier to tell. I'm going to rewrite those derivatives. Alright, let's start again. The first derivative is negative 2 sine of 2x plus pi over 6. The second derivative is negative 4 cosine of 2x plus pi over 6. The third derivative, I'm going back to sine, so it would be 8 sine of 2x plus pi over 6. And the fourth derivative, we're going to cosine again, so it would be 16 cosine of 2x plus pi over 6. Now, the formula we're looking for is f to the fourth derivative, over 4 factorial times x to the fourth. And our question is, what's the maximum value of f to the fourth of z? Alright, I told you that if you end up with sine or cosine, that 1 is the maximum value. This one is different because we're talking about 16 cosine of something. So that means the highest value that that particular graph would approach would be 16 because that's the amplitude. So we're going to get 16 over 4 factorial times 1/3, because we talked about how that was x, to the fourth. And there you get 0.008. That is less than 1 over 100, and that's what we were trying to prove. We were trying to prove that the remainder was less than 1 over 100, and we did because we got 0.008. Alright, the last problem, again, I think I'm going to write it on the slide just to make sure that I have room and so I don't squeeze it all in there. It says example 4. It says that we have a function and we're talking about the third degree polynomial about x equals -2. It says that the fourth derivative satisfies a crazy equation. The fourth derivative of x, it says this, the fourth derivative of x is less than or equal to 25. That's important. I'll show you where in a minute. And it says find the bound of f of -1.6. So it says that we found the third degree polynomial. That means if I want to find the error or the remainder, that I have to find the fourth degree over 4 factorial times, normally it's an x to the fourth, but since it says about x equals -2, then I'm going to plug in x plus 2 to the fourth there. Alright, the cool thing here is I don't have to try to figure out what the fourth derivative of something is because they didn't tell me the equation, but what they told me was that the fourth derivative was less than or equal to 25. So that means that 25 goes in for the fourth derivative of z. Leave the 4 factorial. We know that x is -1.6 because that's what we're trying to estimate. And we get 0.026 repeating. And so that's the remainder. Okay, I'm going to do one more example, and that's not on your sheet. If you want to do it on the back or on a separate sheet of paper, then that'll be okay. Example 5 is going to be one where you don't just put a 1 or whatever they give you. So let's say that we have e to the x, and we wanted to estimate the error for e to the 0.5. And we want to do it for, let's say it was for the second degree polynomial. So that means that I need to find the third degree polynomial. It's always one more. The third derivative over 3 factorial times x to the third. And it would have to tell you that c was 0 or that you wanted to center it around 0. So that's why it's x to the third and not like x minus 1 to the third or something like that. Alright, because we're talking about e to the x, I know that the third derivative is e to the x. Now, because I'm trying to estimate what this is,